Hello students, the question here today says figure below shows a smooth track, a part of which is a circle of radius capital R. A block of mass m is pushed against a spring of spring constant k fixed at the left end and is then released. Find the initial compression of the spring so that the block presses the track with a force mg when it reaches the point P where the radius of the track is horizontal. Yes? Let's understand the situation of the question first. See what is happening. First, we are pressing the spring using the block, let's say by an amount x. When we do that, we are essentially creating a potential energy in the spring, right? Now, when the block is released, the potential energy of the spring will convert back into the kinetic energy of the block, and let's say the block starts moving with a velocity of v0 after getting released from the spring, and it is this velocity v0 with which the block will start moving up this circular track. As it moves up the track, it will lose its kinetic energy at the expense of the potential energy that it will gain as it moves up, right, as it gains height. In fact, if we look at the point P, which is at the same level as the center of the circular track, understand that the point P is at a distance r above the horizontal level, so that the block would have gained some potential energy here and would have lost some kinetic energy in the process, right? But understand that since the track is absolutely smooth, the conservation of energy principle is applicable, right? So, this is the first part. We can use the law of conservation of energy to connect the potential energy of the spring with the initial kinetic energy of the block, and that with the kinetic plus the potential energy of the block at any point during the course of its motion on the circular track. So, let us do that first. We use conservation of energy between the starting position of the block, which we can call as the point A, and let us say the point P, where the block is absolutely moving in the vertically upward direction because it is at a position on the track where the point P is on the same horizontal line as the circle, as the center of the circle. So, conservation of energy between the points A and P will give us, understand that if half kx squared was the potential energy stored in the spring, because the spring was initially compressed by an amount x, which we have assumed, all of that gets converted into the kinetic energy of the block, starting kinetic energy, initial kinetic energy, which will be half mv0 squared, and at the position P, that same energy will now be a new kinetic energy half mv squared, where v is the speed of the block at the point P, plus the potential energy of the block, which if you look at it carefully, mgh, h the height of the block from the ground level is nothing but r. So, it will be mgr, the potential energy, right. Now, let us talk about the second aspect, which is that of the force with which the block presses the track at the point P. See that since the point P is such that it is at the same horizontal level as the center, here when the block presses the track, the force will be absolutely horizontal. It will be like this, right, which is told to be mg in the question. Do you understand that this force is nothing but the force of normal reaction, equal in magnitude to the force of normal reaction that the track will exert on the block in the opposite direction to this force? As the block presses the track also presses the block back using the Newton's third law with a force N, the normal reaction, which in this particular scenario will be equal to mg as given by the question. So, N at the point P, the normal reaction at the point P is mg, and the normal reaction acting on the block is towards left, which is kind of a force which is a radial force which is acting towards the center of the circular path in which the block is moving, right. So, we can use the force equation on the block at point P to find out the relationship between this normal reaction force and the velocity of the block by writing the force equation here. We will just draw the diagram once again to understand this clearly. Let us say this is the circular part of the track and the block is over here, and this is the point P. We are saying this is the center of the circular track. Normal reaction will be acting like this, right towards the center, and the block right now is moving with a speed v. Understand that the only other force acting on the block would be the weight of the block mg, which will be acting absolutely vertically downward and will have no component along the radial direction. So the weight of the block does not play any role along the radial direction. So what we can do here is we can write the force equation at the point P along the radial direction on the block, of course. When we do this, let's see what we get. Net force towards the radial direction, if we see, is nothing but N, and it is this force that provides all the necessary centripetal force that the block requires at this point P, since it is moving in a circular track. Yes. So net radial force N is equal to mass into the radial acceleration or the centripetal acceleration, which we know by definition is square of the speed by r, the radius of the circular track. So this is how we will be able to relate the normal force with the speed. And now we know that the value of normal force at the point P is nothing but mg. This is given in the question. So we can use this information here. N becomes mg is equal to m into v squared by r, and this gives us the value of v squared in terms of r. G into r becomes the value of v squared. Now how do we use this value of v squared? We can take this value of v squared and put it back into this equation above and relate x, the compression in the spring, with this particular term. So what we are going to do now is we are going to use this energy conservation equation once again. We will write it once again starting from half kx squared. We will omit this middle term because we do not really require this. So half kx squared is equal to half m into v squared can now be written as gr plus the second term mgr as it is. So half mgr plus mgr will be 3 by 2 mgr, and now we can simplify this for the value of x. From this equation we can write x squared is equal to 3 mgr by k, and x correspondingly will be root of 3 mgr by k, which is our final answer.